Hi everybody, this is Eugene O'Loughlin and welcome to my series of short how-to videos. In this video we're going to learn how to test for equality of variance in R. Now many statistical tests rely on sample variances being equal or perhaps being not equal. So for example, if you want to compare two samples in, say for example, a student's t-test, to compare the population means of using two sample means, we need to first of all know in some cases as to whether the variances are equal or not. So let me take a look in a diagram to show you what I mean here. So if you want to compare two samples in a t-test, there are different types of t-test formulas in use. So first of all, we determine that there are two samples, in which case a t-test is appropriate, and of course don't forget they should be normally distributed. And there are two possibilities: either the data are independent or unpaired of each other, or they are dependent or paired on each other. When we look to calculate a t-statistic for an independent samples unpaired t-test, we need to first of all determine whether variance is equal or unequal. And without going into too much detail here, if you examine these formulae here, you can see that different formulae are being used to calculate the t-statistic depending on whether variance is equal or not. So therefore it's important to determine whether variances are equal or not using an F test for equality of variance. So that's what we're going to do in this video. So let me switch back to R, and before we do it, let's set out our null and alternative hypothesis. The F test for equality of variance is a statistical test just like all others, so it needs a null and an alternative hypothesis. And in all F tests for equality of variance, the null hypothesis is that the sample variances are equal, and in all of these tests as well, the alternative hypothesis is that the sample variances are not equal. The simplest way to calculate the F statistic is to determine the variance of both samples and place the larger sample variance divided by the smaller sample variance, and that will give us an F statistic. So this is the easiest way. We'll do that in a moment, but we'll also use an R function to do this as well. We're going to conduct our test at an alpha value of 0.05, and I've previously worked out, using the degrees of freedom from the sample data that I have going to use in this video, that the critical value for F is 1.525. So if our F statistic calculated is greater than 1.525, we can reject the null hypothesis. However, if it is less than 1.525, in this example, it won't always be 1.525, the sample variances will not be equal. So let's go ahead and read in some data. So let me read in a data file called 85 data file. It's a CSV file. And don't forget that this file and all other CSV files, plus diagrams and R scripts used in this series of videos, are available in my GitHub. You'll find a link to that in the information section beneath this video on the YouTube page. So let's read this data in and then display it using the print function. So what I have here are body temperatures in degrees Celsius taken for a sample of 64 men and 62 women. So these are the values placed here. And one thing we do need to take note of here at the end is that because the sample sizes are different, there's just 62 women compared to 64 men, when the data are read in, the last 63rd and 64th values for women are treated as missing values. So we're going to have to take into account of that during our calculations. So let's go ahead and use the simple test formula that you see at the top of the R script here. So I'm going to create a vector called F statistic. I'm going to assign it simply the variance of men divided by the variance of the sample of women's temperatures. So I'm going to use var is the function for calculating variance of a sample, and my vector is called body temp. $, I'm going to put the men first and then divide that using the division symbol by the variance, open and close brackets. Let's fix the typo there, open and close brackets. Body temp again is my vector name, and $, and this time put the women in. Now I don't know yet whether the variance of men is larger than the variance of women, so I'm going to just do the calculation first. If it turns out that the variance at the moment, I'm assuming that the variance for men is larger than the variance for women. If that's not the case, we just simply reverse these in the formula. Now, there's one thing we need to do. If we run this line of code as it is, we're going to get an NA, or null value, returned. And that is because we can see in our sample that there are two missing values in record 64 and 65 for women. So we need to take that into account when we're calculating the variance for the temperature of body temperature in women. So I need to go in here and add in a comma and then a parameter called na.rm. So in other words, this parameter here, what it does is I'll set that to true, just T for true. What this does is that if it finds an NA value, RM stands for remove, so it just removes those. So in essence then, it's only going to calculate the variance of records 1 to 62. So let's run this and then display our F statistics. I'm going to use the print function to do that. F underscore statistic. Run that and see what we get. And we've got an F statistic value of 1.162 rounded. So I can see from line 12, where I've previously worked out the critical value, that my calculated F statistic is less than the critical value. Therefore, I cannot reject the null hypothesis. So in my example here, I have found that the sample variances for men and women body temperatures are equal, and therefore that will direct me then to use the correct t-test if I wanted to compare the means of the two samples. Now we can also use, there's a function that we can use here that will also do all of this for us and also take care of missing values and so on as well. And that's a function called Var.Test. Open and close brackets. Now, if you haven't used it before, go to the help section in RStudio, type in var.test, and you will get information, a description, and some samples and usage and what arguments you can use for the var.test function. If you have not used it before, it's always a good idea to check out the help section first. So var.test in here, I simply put in my two variables. So I'm going to put in body temp, $ men, comma, body temp, $, oops, capital should be small p there, $, $women. I don't need to put in a parameter to remove missing values. So let me run this. I've made a mistake here, var.test body temp, I've left out a p, so let's go ahead and try and do that again. And we can see now we're getting a little bit more output than we got before, so I'm going to scroll up here and move the code down so we can keep that in mind. So what we've got here, first of all, is that our value of 1.61743, which was calculated manually, is also the exact same value you get from the var.test function. So no surprise there, but the output from the var.test function gives us a little bit more information. So it gives us our F statistic rounded to 4 decimal places. It gives us the degrees of freedom that the test was conducted at. And it also, very importantly, gives us a p-value. Now, previously at the top of our code here, we had set an alpha value of 0.05. So if my p-value is less than that, I can reject the null hypothesis. Clearly here, you can see that our p-value of 0.5579 is considerably greater than 0.05. Therefore, we cannot reject the null hypothesis, and once again, we have found that the sample variances are equal. We also get some other information in here as well. We've got the 95% confidence interval, so this is the percentage confidence that we would have that this the population F statistic would lie between these two values of 0.7 and 1.9. So that's how you calculate an F statistic using a manual or a function to determine equality of variances in R. I hope you found this video useful. Thank you for your attention.